today's presentation for next an hour or hour and a half. The aim of today's presentation is by the time we finish this presentation, I my aim is to make you acquaint broadly in tunnel construction a little bit, but more so in planning and execution of planning of a tunnel. So initial portion I'll be telling about something about the problems in tunnels, very short, and then onwards we will get into some terminologies of the tunnels. We'll also get into various aspects which are to be seen in tunnels, and then very basic about geology. After all this is completed, then we'll get into tunnel planning, tunnel design, and at the end I have kept around a case study of one of the projects which is presently which has got approved in NHAI. So that is the framework of today's presentation. So straight away we go to the first slide. Okay, if you look at any underground projects, okay, they differ a lot from road projects. One of the main reason why they differ from a road project is anything which is under the ground is very difficult to estimate, and this estimation challenge, what is below the ground, is not only limited to the industry of our infrastructure industry. It is also a challenge which is faced by the mining industry. It is also a challenge which is faced by oil and gas exploration industry. So this underground industry has a problem of finding what is below. And as a result of this, if you look at, I have taken a case of one of the tunnel projects which is completed. If you look at whatever we estimate in a tunnel during a tender stage, if you look at rock classes which have been shown on the slide now in tender, and what you see in actual, you see a variation which comes out, and there is a difference. That difference can be positive, the difference can be negative, but there is a difference, and there is seldom a tunneling project which we are able to complete with what we anticipate. And on the side, if you look, on the side of this slide, if you look, I have brought out a slide from a study which was carried out by Government of Australia and New Zealand, and they had taken studies on the tunnel of all over the globe, including Asia, Europe, Australia, and New Zealand, and road tunnel cost composition breakdown which comes out is approximately 72% of the cost, okay, of the tunnel is based on excavation and support systems which is required in support system which is required immediately after excavation. So that is a broad percentages which it impacts. So if you look at tender rock classes, and if you look at actual rock classes, and if you look at the differences and you relate these differences with the tunnel cost composition breakdown, okay, it has a significant impact, and the impact can be positive as well as negative based on the geology. Now, if you look at another project, okay, if you take in railways consideration of railways also, the particular slide is of USRBL, Udhampur Srinagar Baramulla railway link, and here also if you look, they had huge delays, okay, in this project, and they had a lot of challenges in this project, and most of this project also was based on underground works. Now, if you relate this with the road tunnels, and you look at the pie graph or the pie diagram, which is again from the studies, international tunnel cost studies, which was done by Government of Australia and New Zealand. Okay, you will see that the tunnel excavation cost here also goes around 54%. The difference between a railway tunnel and a road tunnel is that the railway tunnel has a comparatively very less excavation area which is required to be done, because the size of cross section which is required for a railway tunnel is much less than what is required for road tunnel. And hence, this excavation percentage or the cost percentage is around 54% in case of railway tunnel. But the complexities and the challenges which are there in tunneling remains almost similar for both the cases, whether it is rail or road in tunnels. Now, as we move forward, I would just like to show you. I'll just like to show you a video. I have 2 or 3 videos, very short, of 30 seconds or each, where I'll show you the challenges which we face when we do tunneling. This is one of the projects where I was involved in. Now, in this video, you saw that as the flow was happening very fast, okay, the lights and everything had to be cut off, the equipments had to be moved. Now, I just want to show you the same site after rectifications were carried out.
One particular above it. This is colon. कि हम 300 mm का 300 mm इसको बियॉन्ड करने को उसके बाद आपने तो ये सेटिंग लगाना मतलब पहले प्लास्टिक के प्लास्टिक के बाद ये लगे को कॉन्फ्लिक्ट कर दिया कॉन्फ्लिक्ट करने के बाद ये एरिया लिया जहाँ से बियॉन्ड को उसके बाद आपने लेटेज गैडर लगाया था लेटेज गैडर इस टाइप में लगाया लेटेज गैडर लगा के फिर रॉक बोल्टिंग की आपने लेटेज गैडर लगाया फिर आपने शॉर्ट फिटिंग किया शॉर्ट फिटिंग करने के बाद जो लाइन नीचे
Another small 10 seconds video, I want to show another challenge. And then
One, two, three. ज़्यादा नहीं लगेगा बस ये तो मैं अंदर घुस गया
Okay, so if you have seen the last three slides, what comes out of these slides is what you are going to get inside. Okay, can broadly be anticipated, but we really exactly to infer what is going to come out is very difficult. And now again, I will take you to the studies which was carried out internationally. If you look at this slide and you look at all the people who are involved, like the clients, the consultant, the cost estimator, the contractor, okay, all those, and in blue graph is the average. If you look at the prime factor everywhere, which everyone agrees, is that geology is a factor which is a final cost contributor. And at this moment, when I'm talking in year 2024, we are grappling with challenges of getting more clarity on geology. And this is not only in our industry of infrastructure. I'm again stressing it is also in industry of mining and other. Excavation type, if you look, there is a split of opinion. There is a split of opinion between cost estimators, consultants, and contractors. If you look at contractors, they feel there is it's a major aspect of cost contributor. But as you come down, you will see the locality, country of construction, lining type, end use, contract type, and last and the most important point to note is the depth. Are they having a large impact on the final cost contributor? So depth definitely is not. And in fact, Even if you look at other aspects, aspects like contract type, is contract type having a large implication internationally? Okay, no. So the major factor which comes out is in a tunneling is the challenges which an underground underground area which is not visible and which cannot be anticipated. That is the biggest factor which is coming out. Now, if you look at variations because of this geology, and you look at ANZ, ANZ is Australia and New Zealand, AU is Australia, then is New Zealand, then is rest of the world, then Europe, America, and Asia. So if you look at everyone, the estimated cost and the final cost, okay, we have a tendency to look down upon us. But if you look at all over the globe, these challenges are there. Yes, if you look at the graph, this challenge is higher as far as Asia is concerned, and it is comparatively less in Europe. The reason why it is less in Europe is that Europe is generally having a stable geology, okay, compared to what geology you have in Asia. But all across the globe, the pattern is similar. Now, this is another study which was done by the Japanese, under JICA, where they had in Japan they had come out with the cost which is the distribution of cost. And if you look at the pie chart, you will see the support during construction and lining during construction. These two are the major cost which contribute to the tunnel construction, and which goes above 50%, and rest all cost are again I count to around 50% on the other side. Now, advantage of tunnels, it brings out definitely better efficiency, environmental impact is there, safety, weather protection, economic benefits. Don't want to get a detail into it because this is something which we all who have joined this webinar are aware of. But this is the advantages which a tunnel brings out in comparison to any other infrastructure solutions. Now, what I want to get you to is the cost implication of tunnel vis-a-vis road. This is a study which was done in Japan. It was funded by JICA, and the rates which are there are not factored to today's cost, but it gives you an aspect how a tunnel cost and a road cost, okay, can be compared. Now, if you look at them, they have costed for tunnel in both the aspects, or road from both the aspects. One is the cost of construction. Second is also the cost of accident, loss, time loss, money, okay, on account which are some of which are intangible. Okay, so based on that, if you look at cost, okay, the total loss which they have estimated, okay, because of running of the road, money for running of the road, extend law. In mountain road, it estimates around 57 million. Okay, whereas in tunnel, it reduces down to 15 million. Whereas if you look at construction cost, okay, tunnel construction cost is much higher than road construction cost. Okay, almost more than double. Okay, more than double. And then you have a larger cost for repair of disasters in case of road, and lesser in case of tunnels. And similarly, if you look at the total cost, which comes down to around 19 million, and for tunnel it comes to 43 million. If you total up this, what you come across is in mountain roads, definitely, okay, the cost of construction is higher, but cost of maintenance, operations, risk is lower. And overall, if you look, the difference which you get is around 25 to 30% is the cost which is higher on road. So certainly tunnel cost is expensive compared to road. But if you look at tunnel cost in mountain areas, you save a lot, especially if you come across areas which like, let us say, Rohtang Pass tunnel, where you have to climb around 46 kilometers on high hills, having snowfall, rainfall, landslides on those roads, and regular maintenance. The cost in mountain tunnels vis-a-vis a road, you can offset almost to the same. So the cost of doing tunneling in mountains is definitely going to be, or in places which are having a lot of landslides and a lot of challenges, the cost of having tunnel is generally offsetted by rest of the risk which are there. Now, after having a small introduction of everything, what are the challenges, how the tunnel is, now we come to our main topic. Now, if you look at tunnel, this is a cross section of tunnel, and all those who are not associated with tunnel, I just wanted to start initially with the terminologies. Okay, if you look at tunnel, the tunnel is generally, when you excavate a tunnel, tunnel is divided into three parts. The top part, it is called the top heading. In case the larger cross section is there, we do this. We divide the tunnel into 2 or 3 parts and we excavate. If the tunnel diameter is small, as it is in railway tunnels, and it is supported by the geology, then in that case, we go for a single excavation. But if you look at our present tunnels which are coming up in expressways and all, where the diameter of tunnel is huge, okay, this is how we excavate them, especially when the geology becomes poor. Now, if you look here, it is divided into 3 parts. The blue part shows the top heading excavation, which is done in the phase 1. Then you have phase 2, you have bench excavation, which is carried on, and phase 3, you have invert excavation, which is carried out. Okay, so this is how it is carried out. Now we'll go over to the terminologies, various terminologies. Advance, most of the civil engineers will understand. It's how we move ahead in a day. Okay, it can be in one work cycle or in 24 hours. So that is the advance what you take when you excavate a tunnel. Adit, it's a word which has come from hydro sector. It is access divergent to intake tunnel. Commonly, when you have longer tunnels, let us say we have tunnels of more than 10 kilometers or 5 kilometers or 8 kilometers, then what happens is tunnel has only 2 phases for construction, okay, at both the portals. Now, if you start constructing a tunnel of 10 kilometer long from 2 portals, it takes a lot of time for the construction to get completed. So in order to have more phases, the adits are taken into considerations. Okay, so that is what is access divergent to intake tunnel. Then is cover, very critical aspects in tunnel. The cover is above the crown portion or about the roof. Okay, whatever up to the mountain top, whatever particular distance we have, that is the cover, and that's the vertical cover. Similarly, in tunnel, one more aspect of lateral cover. Sometimes when you are driving through tunnel through a mountain, then you should also be very concerned about the lateral cover what you are getting. Otherwise, your tunnel will get exposed and whole things will collapse. Dew fuming. Once you have excavated, the fumes have to be removed. That is what is dew fuming. Drift. Now, drift is another thing which is coming from hydro sector. Okay, unlike the investigations which are happening, here I will also talk a little bit about geological investigations. Unlike the investigations which are happening in road sector, the approach which is taken generally in hydro sector is completely different. The challenges which were faced was that in spite of all methods of finding out what is below the ground, okay, they were not able to come down to exactly what is going to come, and they had their cost implication and everything. So what they did is they started constructing or excavating a small diameter tunnel in the original alignment, and that whole data of that tunnel was used and provided to the contractor, so that the actual geology and the anticipated geology remains very, very similar. The advantage of this method of having a drift was that you really know what you are going to face. But the disadvantage of this method was it was going to take a lot of time, and the project had to be planned well in advance. And during DPR stage or tender preparation stage, a lot of time was lost. Okay, so that was the disadvantage of this. Drill jumbo, it's the main equipment which is used while drilling. We have single arm boomers, we have 2 arm boomers, and we have 3 arm boomers. Not only that, we have boomers with different arms. Also, the level of automations in the jumbos have gone to a very high class. Like if you today look at a 3-arm boomer, you sometimes have a 3-arm boomer which is capable of automatic drillings, and a lot of the processes have become automated. Okay, so as NATM method, the drill and blast method is getting more and more refined. The machineries which are being used, like drill jumbos, are getting more and more automated. Okay, now one aspect which requires to be looked upon by all of us who are in the fraternity is that a 3-arm boomer has larger size. Okay, compared to 2-arm and 1-arm. So generally, if you look in our country, most of the contractors, if you look at our contractors, they will prefer a 2-arm boomer, because of 2-arm boomers, what is happening is you have the versatility of using the machineries in various cross sections. Because if you have a smaller cross section, to get a 3-arm boomer inside, becomes difficult. So generally, because of the cross sectional area, a lot of time these equipments which are selected, when these equipments are selected, the decision on the contractors is not only the using of this equipment for a particular project. They also look into the employability of this jumbos for their upcoming projects or maybe the future projects. So that is one of the aspects which is taken into consideration. Then we have egress. Okay, egress. These are the small tunnels which are parallel to the main tunnel, and which we generally, in a common terminology, call them escape tunnels. Okay, so there are egress tunnels. Then heading benching, I've already explained. Mucking, very simple thing. After blasting, when you take out, that's the mucking. Then you have shaft. When you have longer tunnels, ventilation becomes a problem, so you have shafts there. Then you have shotcrete. This is a type of concrete for people who are not associated with the tunnels. Shotcrete setting time is very, very fast. It just sets in, the initial setting just takes place within a time of 2 minutes or 3 minutes. Okay, that's how fast it sets. The next important thing in tunnel is stand-up time. All these terminologies we'll be using ahead in our presentation. The next one is stand-up time. Now, stand-up time is the time once you excavate a tunnel, you have done a drill and you have done a blast. You expect the geology or the area which you have expected to stand up for certain time. So now, if you have a hard rock, okay, if you have a basaltic rock, or you have a rock with higher UCSs, okay, you will find that the stand-up time of that area is higher. But if you come to poor geologies in Himalayas, you will find that the stand-up time is less. So stand-up time is one of the very important factor which is not only used in design. It is also to be the initial support system what you are going to plan, and how fast and how long can you blast. All this will depend on the stand-up time of a particular geology or a particular rock type. Then we have tunnel lining. Okay, so generally the tunnel lining is divided into 2 parts. When you do a tunnel, other than you are doing a tunnel with a TBM, we have tunnel lining, which is called a primary lining, and a secondary lining. The primary lining is a support system which we do initially, and once we have done a lot of primary lining and we have gone substantially inside a tunnel, and then you are supposed to carry on and your deformations have become normal, then you are supposed to do a final lining. So there are 2 linings which come up. And finally, it is a work cycle. That's the whole operations, okay, of tunneling which is being done. When you complete, that's called one cycle. Now, if you look at excavation cycle of tunnels, okay, initially you start with drilling and blasting. Okay, as you can see on the slide, it is followed up. By cleaning it, and after drilling, you charge everything, charge everything, and finally you get ready to blast. Now, when I'm talking about charging and blasting is a separate intense subject which requires to be focused. And number of places, if you see the pattern of charging and blasting is left down to laborers, or left down to a single man, who has really no great experiences. But charging and blasting is one of the critical factors which are to be taken care of, especially when you are doing your portals, and later on if you do not want overbreaks. I will give you an example of one of the tunnels. I don't want to name the area, where if you look at this slide and you look at the top holes, certain of the top holes have to be left unfilled with charge, and they are the holes which help in reducing the stress. If you can see my cursor and you see this hole. Okay, now suppose I put a explosives here. Okay, this explosive is further going to destabilize my crown of the tunnel. So there are dummy holes which are required to be planned and required to be done. And a lot of times I have seen that on site, what happens is when they are doing excavation, there is no emphasis on the dummy holes, and the stresses which are induced because of blasting, these stresses are transferred into the areas of crown and side walls, and resulting into an implications of either over supporting that, or maybe even collapse of tunnel. So that's very critical aspect, that charging and blasting is a separate important subject and requires to be given importance at the start of a tunnel. So once you have done charging and blasting, then you do ventilation. After ventilation is there and defuming and everything takes place, then you do mucking. After mucking, then you give into support, and that is how the whole cycle goes. And then again you go to survey, and then the cycle continues. Now, this is what happens when you do a drill and blast tunnel. Now, at this point itself, I want to tell the audience that, as far as road tunnel is concerned, why do we favor a drill and blast or NATM method compared to a TBM? What happens is, you all will agree that presently the TBMs which are in operations are generally circular TBMs. Although internationally the research work is on having rectangular TBMs, but presently whatever you get are circular TBMs. Now, since you have most of the TBMs are circular TBMs, if you look at circular TBMs, the largest area which is available in a circle will be always at the diameter. Now, because the largest area which is available is at the diameter, and as far as we are concerned in those road sector, we want the largest area, to be our carriageway, and we want it at the as below as possible in any cross section. So when you compare a drill and blast and when you compare a TBM, you see that the lot of portion below the carriageway has to be filled up in case you go with TBM. And that is one of the reason why in larger diameters, TBMs do not give you that economic values, which you look at, until unless you have tunnels which can be used, which have multi-purpose uses. So that is one reason. Second reason why we go for drill and blast or NATM method is, if there is a regular change in geology, the NATM, the TBM has an inherent disadvantage. That TBM cutters are generally able to carry, are able to address a particular type of band of geology. Okay, so if you have a soft geology and suddenly you come across a rock, very hard geology, presently you require to take out all your cutters and replace those cutters for the harder geology. Okay, initially, if you go another 5 to 10 years back, even these provisions were not were not present. Okay, were not present and TBMs were not catered. But now you can definitely do that. So these are the reasons why TBMs are generally not preferred much in road sector compared to the NATM or drill and blast method. Now, if you look in terminology, I had told you there are two things which we do in tunnels. One is primary support, and second is the final lining. So in primary support, these are the methods which are used. Okay, you use a wire mesh, you use shotcrete, you use rock bolts, you use steel ribs, for pulling, pipe roofing, dewatering, and you use chemical grouting. If you look at this cross section, now if you look at this cross section of a tunnel, and you look at heading, all what you see the straight lines are the rock bolts which are used. Once you have excavated, you are supposed to put in the lattice girders or the I section ribs, okay, or I section ribs along, and then you use all the supports which we are talking about here is wire mesh, shotcrete, rock bolt, steel ribs, maybe some of them, maybe all of them. Okay, this is how it goes through. And then you further, once you have completed, if the geology is very poor, then you require to close the ring. And once you have closed the ring, the whole area of that becomes stable. As you go below, as you excavate below, again you have to excavate this. You have to open the ring. You have to close. You have to go to the bench, and still, if the stresses are higher, you may also have ring and the bench. Otherwise, you may be able to continue to bench and invert. Now, if you look at the cross section from longitudinal aspect, if the construction is done, this is the tunnel face, and presently we are doing the top heading. Okay, so you have to keep a space between the top heading and the benching. Okay, and then comes the invert. So generally, the process of excavation is you do excavation at the top heading. You allow all the convergences to take place. Okay, all the convergences to take place. Like you will install the primary lining. You will install primary lining, and once you have installed the primary lining, okay, you will continue with your next cycle, and you will go ahead. You have to keep a substantial distance, okay, of at least 150 meters or so between the top heading and benching, because you do not want the stresses which are coming due to the excavation here, to immediately get transferred to the bench when you are excavating a bench. So, and generally this stresses can go as far as a distance of around 3D to 5D. Okay, 5D also it can go. And if you take another further cushion areas and working space areas and everything, that is what is kept. And generally distance between a top heading and benching is resorted to between 100 and 150 meters. Once you have done benching, you will see that the benching and invert, the distance is not much, which is not kept much. However, if the geology is poor here also, you may have to keep a larger area. The reason here why you don't have you are doing things in parallel is almost in parallel is the amount of excavation which takes place in bench and invert is comparatively smaller than what you do it in top heading. So that is the reason why these activities are generally carried out simultaneously, because you are aware of the geology, you are aware of the convergences, you are aware of things, and based on the data what you are aware on, okay, you decide whether you can move faster or you can move slower. Now, in some cases, what happens is we have very, very poor geological conditions. Okay, and when we have poor geological conditions, we resort to supporting something what we call is either pipe roofing, or I will use the terminology which I'll say that you try to support the area above your excavation, like the crown area. You try to support it either by grouting or by pipe roofing, or by fore pulling. Now, what is the difference between all three of them? Okay. Now, when you say grouting, some places we used a word called soilcrete. Okay, so what you do is basically you inject various type of material, maybe simple cement, maybe cement and slurry, cement and slurry with microsilica fumes, maybe polyurethane foams. So you have to decide what you have to insert here. Now, the second thing which people do is doing a fore pulling or a pipe roofing. Now, when you say fore pulling are generally the diameter. It's the tall steel rods or rock bolts which are used in fore pulling. But once you come to pipe roofing, it's 76 mm, 114 mm pipes which are used for supporting the crown. So this is how it is done. Now, certain tips I want to give here is this is regarding the crown stabilization. Is a number of places I have seen that we resort to cement grouting. Immediately after excavation, we see there is a flow and we start cement grouting. A number of places, what happens is if you do cement grouting further adds on. It gives. You'll agree with me that if the soil is bad and we add water to it, the soil is going to flow. So similarly, if you have a collapse and you add cement slurry to that, and you do not ensure a proper consolidation time for that cement, that cement slurry, then what happens is it will add further into collapse. So what type of method you use, whether you use a fore pulling, whether you use a pipe roofing, or whether you use a consolidation grouting, or you use a combination of all this, has to be really understood before you apply it. Okay, because maybe you think that it is a solution, but you are adding further into the fractures, by adding these slurries, and you are trying to add the collapse. And at number of places on ground, this basic wisdom is seen missing. Now, whatever I have spoken here, this is what is shown in this diagram. So if you look on this slide, you can see this represents the soilcrete. The outer layers represent the soilcrete. Then you have pipe roofing or something. Then you have shotcrete lining. If you look at side here, in case the stresses are more, wait 1 second, sorry. In case the stresses are more, then what we do is we have something called we increase the area. How we do it for columns, in columns, what we have a base footing. So even in tunnels, what we do is we increase the area of support down and we make elephant footings. Okay, we make elephant footings. So this is how, if you can see my cursor, this is where the elephant footings are there. Sometimes even the elephant footings are not going to take up the stresses. And if that happens, then you have to go for inclined micropiles. So this is a general sequence of primary lining depending on complexities. Okay, you have to design them, and you have to plan for them, and you have to execute them. Now, this slide will give you an aspect of a rough percentages, which will go into each activities. Okay, if you are drilling a borehole, okay, if you are loading a borehole, okay, 9% of time, blasting will generally take around 4%, then ventilation 4%. Then you got to come at the face and do a geological mapping, which takes around 4% of time. Then you have to dumping of excavation will take around 20%. Then shotcreting, support measures. And then again, if you have to do another layer of shotcreting, okay, drill rock bolt placing. So all these percentages are given. These are very rough percentages. Okay, don't take it like Don't take it like an exact these figures, but these are generally tentative times which will be used in a cycle, of working. Now we come to how do you do a road tunnel planning? Okay. Now the first thing which will come is the decision of road type. Whether you are having the road is passing through a city, urban, expressway. So that is one of the basic factors, because the basic factor itself leads into a big issue of cross-sectional area, and that cross-sectional area requires to be supported. That cross-sectional area requires to be supported. So the decision has to be based on that. Then you come to selection of tunnels. Okay, tunnel routes on a large scale map where you look at topography, geology, climate, environment. Whatever I'm going to talk, I'll be also presenting this at the later stage in this same presentation in a case study. Then you go for selection of tunnel routes. Okay, you compare various tunnel routes. Then you go, once you have compared, you finalize the tunnel route, and then you start execution of drawings and various investigation. Why is this important? Okay, number of time what has happened is when we go and we get into interactions with the various officials, we find that there is a dichotomy in understanding, at what stage what is required and how it is to be approved. Because one of the places we face challenges is like, investigation cannot happen in tunnel until unless you finalize the alignment. Okay, once you have finalized the alignment, then only on that particular alignment we can have investigations. But understand the dichotomy. The dichotomy is, if during investigations you come across a very, 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 very challenging geology, maybe that may force you to change an alignment. Okay, however, the amount of percentage you come to this such type of decision is very, very rare, because any tunnel in any form of geology, whether you want to do it undersea, you want to do it in a poor geology, you want to do it in a good geology, a tunnel can be constructed in all type of geologies. So one thing is very clear, that you can do it. However, what happens is, if you have poor geologies, the time of excavation, the amount of cost which goes into supporting, and the challenges which you will face will be higher. So that is the reason we try to avoid. So what is important here is, unlike planning of a road, the planning of tunnel, the stages are do not match with the stages which undertakes in either planning of a bridge or in planning of a road. Now, when we talk about this, we'll slightly elaborate alignment selection. Okay, alignment selection, I said the factors which are going to impact are going to be geological, geotechnical, hydrological, and environmental. Okay, these are one of the primary things. Now, if you look at geological and geotechnical considerations, okay, world over, the amount which is spent on this varies to around 3%. In our country, the amount we are spending is approximately less than 1%. And based on that 3%, now even if you go to international standards, okay, and you look at large tunnels like Gotthard, okay, 57-kilometer tunneling was done. Okay, now in Gotthard too, what has happened is, in spite of all geological and geotechnical investigations, they had problems in two tubes which are running almost parallel. Okay. So what I'm trying to say is, when you do investigation of even 3 or 3.5% or 4% expenditure you do, imagine you have to interpolate something which is 95, 96, 97 or 98%, okay, which you have not investigated. Drilling, which is the most important aspect of investigation, gives you a bore of approximately, for people to understand, gives you a bore of around 5 centimeters. Okay, that's the core you get out. Okay, now if you imagine you have a tunnel of 3 kilometers and you have done number of borings also. Okay, still the area what you get is only 5%. So what I'm trying to bring out here is, and in this geological and geotechnical consideration, presently, whatever's are the methods of explorations, they are based on two factors. One factor is one factor of finding out what is below the surface is either by sending a sound waves down and getting a reflection of sound waves. The second factor which is used is the electrical. Okay, you have electrical and electrical resistivity, and based on that resistance, you come to know what it is. Now, whatever said and done, you will have a lot of people saying that you can do an aerial lidar and you can do this, you can do resonance, you can do that. But please go and see on Google and search in Google, you will find that whatever technologies are available, they cannot penetrate beyond a certain depth. Okay. Hence, even if you want to do like you suppose you want to do a very deep down, you want to take a sound reflection, so you'll have to dig a hole, or you'll have to dig a borehole, and then you'll have to send the sound waves, and then you'll have to receive those sound waves after that borehole, and then only you will get the bottom portion. So what I'm bringing out, what I'm emphasizing here is, till today, although the technology has evolved, but still it is not been able to replace the human expertise and human understanding. Maybe in years to come, this human understanding and capabilities, now are getting into algorithmic forms, and we are going to have, it's going to come out in AI. Maybe the human deficiencies, will be able to offset this human deficiencies, across other people by this, by AIs. So maybe then your interpretations may get more finer and all. But till date, whatever technologies are there, they are still short. They are still short to let you know what is going to be below. Okay. Once that is done, then horizontal and vertical alignment, I'll not get much into it because most of you are road people and you understand that. Then our next aspect is going to be cross-sectional profile, shape, size, and clearances. Okay. Now, in tunnel, shape and size. Okay, there are slides ahead. Shape and size matter a lot. Shape and size matter a lot because the shape and size affect the way you will transfer the load. So if you have an arch formation, like let's say you want an arch, and in arch, if you go, let us say if you go for a D shape, okay, or you go for a horseshoe shape. Now these shapes are affected by the geological consideration because these are the shapes which are going to transform the load. Okay, so if you have a good geology, you may go for a particular shape. If you don't have a good geology, maybe you will have to refine those shapes and you will have to refine your arches and accordingly come to that shape. So shape plays a very, very important aspect in tunnel. Size is beyond our control because whatever purpose that tunnel is going to be made, you require those dimensions, you require those clearances. So sizes are generally beyond the, but the shape is an important factor. And whenever we do a DPR or whenever we are planning a tunnel, this aspect can increase your cost and can decrease your cost in your support system. So once you are thinking about shape, it's not like you just take any cross-section profile and try to use one cross-section profile, the same cross-section profile everywhere. The next salient aspect is safety and ventilation. Okay, safety and ventilation. So safety, if you look at safety, there are emergency exits. Okay, so there is a lot of debate in this. When we go to the case study, we'll come to it. Like, you should have a single tube, you should have double tube, whether you should have escape or you should not have escape. That is a big question which comes out. Another aspect which comes out is ventilation systems. Okay. Presently in our industry, if you look, we are, everywhere we are trying to say now, get into mist systems or get into, initially it was sprinkler. Now we are trying to get into mist system. But do understand that ventilation accounts for a large amount of cost, not not during installation. Installation, when you are installing a ventilation, your cost generally varies from around 17% to 22%. Okay, that is the amount of cost which will go into installation of ventilation system in a tunnel. But the operational cost of a tunnel for 120 years, okay, that's the life of structure. The operation cost of ventilation has to be taken into consideration. So when we look at ventilation system, and when we are thinking of putting everything what is modern, okay, maybe that is not required. Okay, I have seen number of tunnels which are having shorter length. Okay, let us say 2 kilometers or lesser than 2 kilometers, and people emphasizing on mist system. Okay, and the tenders or the DPRs are made where people have just put the mist system. Imagine, it was not required. It was not required, and it is something like you require a hammer. Let us say hammer of 1 pound, and you have got a hammer of 100 pounds, and you are trying to break a thing. So ventilation systems do require in our country a lot of deliberation. First of all, the expertise is less in this area. Because this is a mechanical domain, and it is a mad rush of just trying to say what is the latest. Okay. Then we talk about structural support system. In coming slides, we will be talking on that. Finally, we come to another debatable topic is seismic consideration in tunnel. Okay, seismic considerations. Now, seismic consideration, do understand one thing is tunnel is one of the most stable structure as far as seismic considerations are to be looked at. And you will be amazed to know that the areas where this seismicity is going to affect your tunnel is generally maximum at the portals. Okay. So first thing what I want to drive home here is that the seismic consideration vis-a-vis any other structure in civil engineering, where other civil engineering structures is the least in tunnel. Second thing what I want to put across is it in tunnels, the impact will be more on the portals. So hence most of the tunnel designs when you are doing, okay, you have to be very cautious when you are doing your portal designs. Another aspect which is very important is construction method. Okay, now construction methods and construction techniques. Okay, now if you look at drill and blast, okay, drill and blast itself has like, let us say, excavation technique. Excavation technique can be heading benching inward. You can call that one excavation techniques. Okay, or you can also talk construction method, like we have in drill and blast, we have various type of methods. We have Norwegian, we have Italians who have done Edico RS. Okay, we have NATM, and we have traditional old drill and blast. When I see this industry, is the people do not run on philosophies. Okay, like if you see a Norwegian method, and you see an Edico RS, that is the Italian method, and you see an NATM method, I would just like to explain the difference between three is. In NATM method, what happens is you design as you go, and you try to utilize the soil or the geological or the rock mass properties which are there, and you try to make an arch of it, and you try to use the same rock mass or the soil mass which is there, you try to strengthen it, and you try to make it an arch, and you allow the deformations to happen, and you support it. Okay, so that's the philosophy. So philosophy of NATM is you allow the deformations to take place, and you use the material in situ materials, and you try to strengthen them, to take loads. Now, if you come to Edico RS method, okay, what Edico RS does is they say no. Okay, we do not require anything to be converging. So what they will do is they will grout all the faces. They will support the face in such a way that the convergences are very minimum. Okay, understand one thing, there will be convergences, there will be deformations, but what they do is they grout whole area, they grout whole face, they will strengthen that, and then they will excavate. The third one is Norwegian. Okay, Norwegian runs on the concept of both ADICO-RS as well as NATM. Okay, what they do is they will say that you don't require to do a final lining in most of the cases. Okay, and what you do is you do a partial grouting wherever required, and you do initial and you have a initial lining support, and our method is faster. Now all these three method they say that we are faster, we save a lot. So if you look at ADICO-RS and NATM, people say that the NATM people will say that NATM is cheaper, the ADICO-RS people will say that is a cheaper. So when you look at tunnel and when you design a tunnel and when you look at excavation techniques, you should be very, very clear what you are doing and what is your philosophy. Now, if you have a philosophy of allowing the deformations, then your support systems have to be made like that, and you have to have that philosophy and you have to have that thought process. I have seen in number of tunnels which are happening in our country and especially in northeastern side. Okay, there is a blind shift of using I sections to support. Okay, I sections become comparatively a rigid support system compared to lattice girders. Okay, so we should know for what design philosophy what we are using. So it's a very important aspect. The next aspect is drainage and waterproofing. I will show you this with some slides in later, so I don't discuss much here. Lighting and signage and monitoring and maintenance is another factors which are to be looked into. Now, flow of investigation. I think we can just go ahead from this slide. Okay, now we go to geology. Okay, geology is one of the major aspects in tunnel. And the biggest part of geology is that there is no no exact numbering or value. Like let us say when you design a structure, like let's say when we design a building, and we talk about loads or we talk about anything, we have an exact figure. This is 10 ton, the live load is going to be this much, and overall this load is going to be this much. But when you come to geology, the things are in bands. Okay, and they depend on a material which is anisotropic. Anisotropic means the way I look at the material, the way you look at the material, and the direction I look at the material, and the direction you look at the material, okay, is going to define that material in a different way. Okay, so let us say I see a geology from a face, okay, and you see it from another angle. So when you see from a different angle, what is going to happen is the incline of slopes, the incline of everything is going to be in a different dimension for you. It's going to be a different dimension for me. The impact of those joints, okay, if you go in a different direction, you're tunneling in a different direction, will have a different implication of that. Now you look at the same rock properties, if you look at from front and behind, okay, or different angles, what will happen is the same geologist, different geologists will come to a different figures, and these figures will be generally in band. So geology interpretation at this moment has is something, the material you are handling is something like that. So that is one aspect which we have to understand. Now, if you look at geology, it depends on mineral texture, composition, then it depends on joint, it depends on their properties, its patterns, its density. Okay, and all this, when you look at and you combine all this, then you get a rock mass. And then this rock mass is supposed to have certain amount of inherent strength, which you want to further support, and then make a support system. So that's how whole thing moves. These are some terminology which we use in tunnels is hard rock, soft rock, or soft ground. Okay, when you come to soft ground, then you say raveling, firm, fast raveling, slow raveling. Okay, so there is a standard terminologies which are used when you define a. Generally, you will find that when you define this, the definitions itself are very complex. So there are standard ways of talking about geology. Now you look, just to give you an example, okay. Now just to give you an example, okay. Here I have shown you two types of geology. If you look in A, okay. If you look in A, it makes something like an arch. Okay, so naturally, if something is made like an arch and you drive through this geology, what is going to happen is it's going to self-support. Whereas if you look at geology, which is like this, okay, in case of B on the slide, okay, if you try to go through this, the collapses are more. So whatever I told you before, this is a very simple way to present that, you know, how the geology will affect, and compare this geology with whole alignment, and be sure that you're not going to get a particular type of, you know, joints all throughout. The joints are going to change. Okay, now based on those joints, your support system, like, you know, your rock bolting has to go down. Let us say if you take case A, you know, you may have to think, you may have to think how you'll apply your rock bolts in a different way. When you look at B, you may have to think in different way. So joints, rock bolting in tunnel is not something like, you know, if the designer has put it at every direction, you have to align your, when you do it on site, you have to align it with the joints, you have to think about that, and then you have to support. So that's the complexities which underground structures, you know, have to face. Now, these are the various tests. Okay, these are the various tests which you require before you do. Okay, so you require geotechnical parameters, you require primary stresses, you require geophysical properties, you require strength, Young's modulus, swelling potential, okay, abrasivity. With all these details, you have to get into your software, you have to put it, you have to come to loads dynamics, and you have to understand this from the perspective of things becoming anisotropic and things being in band. Okay, so that results into experiences, which is required in a tunneling this. Okay, now these are some of the primary methods which are being presently used. Okay, we have field mapping, exploratory borehole trial field. Then there are geophysical, you know, ERT, SRT is there. Okay, ERT, SRT is there. Then various other cross borehole tomologies. All those things are done. Then field test is there, laboratory test is there. You know, all this when you do, and when you get the details for, you know, for this, from this investigation, you get this, then, you know, you are able to put everything in a software and come out with designs. Okay, these are some additional tests which are required. Okay, if required, depends on that area. Okay, and basic studies of that area. That's the gas occurrences, if there are creep movements, neotectonic occurrences, temperatures, seismic activity, okay, substance generating health hazards, radioactivity, residue. So these are under ground hydrology, okay, or even ground contamination. This is what something else is required. Now, if you look at our IRSP 91, okay, the present 2019, it is under revision. Okay, if you look at, this is what it talks about. Okay, it talks about that in tunnel. Now, this is an advisory which is given. Okay, number of places, what is happening is we take it, you know, we take it that this is where you have to do it. See, when you do a borehole, you know, before you do a borehole, you should have completed your primary geological mapping. You should know where your geology is changing, where your faults are, okay, where your faults are, and where are the places from where you have to extract data, so that you can make a L section which is going to be, you know, which is going to be of use to you. Like, let us say we start a tunnel, and within 50 meters of that tunnel we have a fault. Okay, at 1/4 of the tunnel, then from that fault, let us say to half of the tunnel, we have the same geology. Okay, so now if you look at, I require a portal, I require investigation at portal, I require an investigation at the fault. Okay, because there is a fault. Okay, then maybe the rest geology, you know, if it is having it's a better geology and it is having this, maybe I require only one borehole there. So it is not a mathematical way that, you know, you can just divide and you can take samples. And this, whatever you are doing, then this has to be supplemented by your geophysical. Like, maybe you are doing a drilling somewhere. You want to confirm it. You want to confirm. Let us say you get water there. You want to confirm it with ERT, SRT. Okay, maybe you have a philosophy where you have done 2 boreholes, and in between what is there, you want to, you know, do ERT, SRT to find out that. So what I'm trying to say is, initially mapping that area applying your studies on the by taking out the details from the Geological Survey of India, ground, what tectonic activities were there, how that formation is, understanding whole that thing. Then you have to plan your investigations. Okay, so the investigations in case of underground work cannot ever be a mathematical. Okay, so that's the point I want to drive here. Another aspect which I want to come is various type of drawings. Conceptual, preliminary, tender, final. There is a lot of confusion that people feel that tender design will be a final design or preliminary design will be a final design. Imagine this with inotropic, and imagine this with you are not aware of whole tunnels. Okay, now your investigation is 3%. You can't have a final design by that 3% or 2% of investigation. Okay, as you go, you will have to change. Another aspect is tunnel classification as per SP91 is 500 to 1500, and long tunnels are generally taken as 1500. Now, unfortunately, we do not have division of tunnels, urban tunnels and rural tunnels or remote area tunnels. Okay, and all our calculations, are based on let us say when we talk about when you have to give escape tunnels and all, are based upon very conventional European methods which we have used in India. Okay, we have yet to Indianize them. We will just bypass this and go over to okay. Now tunnel design aspect, one more critical aspect is cross passages. Okay, we have cross passages, and if you look at this cross passages, you have cross passages either oblique or perpendicular. Okay, IRSP 91 gives you option of both. It is easier for a contractor when you go at 90 degrees, and it is better in weak geology to go for something which is at 90 degrees. But if you come to a stable geology, then you should go one which are at oblique, because it is easier for flow of traffic, and it is easier. However, it is difficult for construction. So since the geology is good, then you have to go for oblique. So oblique is convenient for geology, is convenient for the traffic, but uncomfortable for excavation. Okay, and if you go for perpendicular, then it is easier to excavate. But it is uncomfortable for the geology. So that aspect has to be looked into. Then various shapes. Okay, various shapes which I was talking about, influence of the shapes. Okay, so these are the various shapes which are generally required. Okay, these are the photographs of those. Now, major design items, you have to do horizontal alignment, you have to do longitudinal profile, fixed cross section, auxiliary, rock mass classification, geometry. Okay, I don't think I require to explain much about this. The second aspect is you have to understand is that design, there are various methods, analytical, empirical, observational, and numerical. Okay, ABC, analytical, empirical, these methods are generally empirical, and observational methods are generally based on researches which were done earlier by Barton, Hook, etc. Okay, they had they had studied number of tunnels, and based on that, they had come up with the support system, and that was happening. Now we are into numerical method, where you do numerical analysis of things, and then you come out with a support system. Okay, now in this slide, if you look at, these are the general guidelines which we require: pavement of camber, edge strip, okay, paved shoulder, design barriers, railing heights, cross passages. Now here, two aspects I want to highlight is at number of places we have got a railing height of 900 mm. Okay, and if you look at tunnels, these are still being planned at 900 mm elevated footpath on both the sides. Understand in tunnel, the critical area is escape during emergency. So if you give an elevated railing height, it becomes an obstacle for people to escape in case of fire and emergency. Okay, hence it is not advisable to have it at that. It should if you want to segregate the traffic of road and traffic on the footpaths. Okay, it is better to have railings railings dividing them, then to give it a giving a height of the footpath. Okay, at this moment, number of tunnels are being still designed with that. Okay. Another aspect is if you look at cross passages at every 500 meter. Okay, now this is one point number one is 8 is one which decides beyond what length of tunnel you require to have escape tunnel, because as per ISP 91 or even internationally, they say that you have to be in case of an incident, one should not be made to walk more than 500 meters. Okay, so that parameter transforms that, if it is a 1 kilometer tunnel and in the center there is a incident, you have to walk 500 and you are out of it. Okay, you are out of it. So that is the reason beyond 1 kilometer you have escape tunnels which are coming in. Okay. Now, if you look in guidelines of tunnels, if you look at guidelines, you can come up with various combinations. Option 1, 2, 3. Okay. Now, option 1 is what you can come up with single tube with escape. You can come with twin tubes. Okay, where the lane widths are 3.5. You can come with twin tubes where you have a unidirectional lane. Unidirectional lane of 5.5. You can come up with optional unidirectional of 3.75. Why I'm showing you this is during design stage. Okay, during design stage, you have to resolve this planning and you have to come to a conclusion what you want to do. And if you relate this again with traffic capacity, okay, if you relate with traffic capacity, whether you want to have a single tube or twin tube, these are the factors which are taken into consideration to decide that. Another important aspect is drainage aspect. Okay, if you look at drains in tunnel, okay, if you look at drains in tunnels, you have to take out the water. Number of places, if you look at your one of the major tunnels which we have, which is connecting Srinagar, Kazi Kund Banyal, you have drainage which is planned in the center, and because you have planned drainage in centers mean in the carriageway, you have manholes, you have manhole covers on top of it, and then traffic is flowing over that, and that is resulting in results into a lot of wear and tear of those manholes and the areas there. Okay, the recent international concept is that drainage has to be totally, your carriageway should be out of any manholes, any coverage, and you have to shift it towards the sides, and then whatever you want to take, you have to, if whatever you want to take, you take down, but there are no manholes and there are no man covers for that. This is how the drainage aspects and drainage aspect is looked into, and this is how the water is taken. It is taken on side. Okay, this is the old concept. This is a railway tunnel, so it's the old concept of railway tunnel. So nowadays what we do is from here, whatever, if you require any additional water to be connected, then you connect it to the main tunnel. There is no manhole. There is nothing on top. This is how its excavation takes place. Whatever you see orange, initially you make an abutment. Okay, now you see the green portion. Okay, so you make that, and there is a no fine concrete and everything you pour. After that, you have this waterproofing membrane. You see this darkish red line, dotted line. Okay, so you construct that, and then once you have fixed them, then you straight away go for your final lining. Okay, so when you do a tunnel analysis, you have to decide whether you want a watertight tunnel or you want a waterproof tunnel. Okay, a watertight tunnel will have absolutely no water coming in. Okay, and it has to take in, if you want, in certain tunnels you have seen in our country also, we have only tunnels, certain portion of that has been done into waterproofing has been done, and balance of the tunnel has been left, and later on what has happened is the water flow shifts from one direction from one place to another place, and then we are having like leakages in those tunnels, especially in Himalayan tunnels. I think one of our tunnels where we have this problem is in Rohtang. Okay, then lighting. Okay, lighting, you have this is a longitudinal section. So when you get inside from outside, you have to have the maximum lighting. And then as you get inside in your darker zone, the amount of light has to be reduced, because here you will get into blind zone. That's how it has to be. It has to be planned. There are softwares where you have to put in you have to put it either Dialex, Dialex and other softwares also are there, where you have to put in and you have to, get the intensity of light. You have to compare it. You have to look at the direction of your tunnel portal. You have to compare that direction with the direction of your rising of sun and closing of sun, and based on that, the whole tunnel lighting design has to be done. Okay. When we come to fire, at this moment we have a lot of debates which goes on, and people are talking about fires up to 200 megawatt and all. Generally, Europe has designed everything on 50. Okay, but when we come to India, we are still talking about 200 megawatts. The recent international codes have started reducing this amount of this fire load and everything. So you have to and understand the impact of fire loads. Impact of fire load is not only in fire. The impact of fire load has impact on your thickness of your concrete lining. And because it has impact on your thickness of concrete lining, it has impact on your excavation profile. Okay, so whole of this is related. So it has impact on your construction cost. It has impact on your maintenance cost. Okay, so when we look at tunnel fire aspects, we should be very clear what we require to do. And these are the present norms which people are going through. Okay, then ventilation system can be during construction, during operations, nothing much to talk about this. Okay, this is the amount of, this is the amount of fresh air which you require to give. These are the norms. And these are the maximum allowable concentration of various, obnoxious gases which can be inside. This is how you plan, you plan your during construction. You try to push out fresh air through a ventilation pipe where you are working on the face, and the extraction of fumes automatically takes place here. The concept is to provide fresh air to the people who are working at the face. That's the concept during construction. During final ventilation, you have to think, if your tunnel is too long, you have to think about shafts, and you have to think about how you plan on shafts, and you take out the gases. Cross passages already I have explained, so we move ahead from that. Okay, we have talked about this also. Okay, then in tunnel you have various types of ventilation. Longitudinal. If you look at longitudinal, you simply have fans, and you use a single direction way of flowing of air. That's how the longitudinal ventilation runs. Okay, that's how the longitudinal ventilation runs. So you have a fan, and in one direction you have flow of air. But if you come to semi-transverse, okay, what happens is you have a duct on top, ventilation duct on top, and from there you will push in air, and you can take out the air from the both the portals. That is another concept that is called the semi-transverse. When you talk about fully transverse, what is happening is you have the concept of taking out the pollution air, and you also have concept of pumping in a fresh air. Okay, so if you look at last two areas, the concept was to take out obnoxious gases. Whereas in transverse system, you have a concept of first pushing in fresh airs as well as evacuation of obnoxious gases. So this is a broad way of looking at longitudinal, semi-transverse, and transverse system. This is in case you are using a shaft. Okay, the green line shows how the fresh air will come, and red line shows how the obnoxious gases will be taken out. Okay, now in another 5 minutes to 7 minutes we'll finish this, and that will be the end of our presentation. Okay, we already spoken about this. Okay, so this is what you have to look: alignment, cross section, everything. Now these are the various things you have to go through: documents, geological studies, topographic survey, and even our codal provisions. You have to go into around 3 or 4 codes before you finally decide what you have to do in tunnel. So IRSP 91 leads it, then 73, then 48, and 84. Okay, now in this is a particular case which was this is a particular case of work which was done for NHAI. Okay, for NHAI, and it is general area of Mussoorie. Okay, if you look here, you have to virtually read about whole. Initially, you have to read about whole area. What type of formations are there. If you look at this, you find out these details. You look at which geological area they belong to. So you will broadly come to know, what you are going to face. So this desk study has to be done. This mapping has to be done on ground. Okay, once you have done this, then you have to look at these faults. If you look at my cursor, these are all the faults. Now, if you look at faults like this faults, definitely when you plan a tunnel, this area has more faults, so you should not plan a tunnel on this faults. Okay, this has little less faults, so you have to plan your tunnels here. Okay, now when you are planning a tunnel, you should not plan a tunnel right below the fault. Okay, if you plan a tunnel below the fault, you will have more complexities to come in. Okay, if you have to encounter a fault, you should try to encounter a fault, at 90 degrees, so that you have a fault only for last thing. So this whole study has to be done on the desk. Once you have done this desk studies, then you have to find out in that area. You have to find out what geology you had, what you did not have. All those has to happen. Then you have to mark your ridge line. Okay, we have to understand that our ridge lines are the most stable in that geology. Okay, that is the reason they have formed that there was a resistance, and that resistance has created the ridge lines. Okay, so those ridge lines are the areas which are the easiest to excavate. So as below as a ridge line you are, or as diagonally to a ridge line you are, that are the two best alignments. Best alignment option which is required, which is one should go through. Then you have to plan your entry zones. You have to plan your exit zones. Which are the possible entry zones, which are the possible exit zones. Okay. Once you have planned those entry zones and exit zones, you have to go on site. You have to survey all those entry zones and exit zones. Okay, this is how it has to be done. Once you have done that, then you have to zero down to the entry zones, which are more conducive, and you have to go and start looking for the portal where your portal can come. Okay, so it may not be the best of the geology, but in that particular area, it should be the best of geology that you have to look out for. Okay, based on that, then you will have various alignment options. Okay, each of these alignment options have to be studied, verified from the ground, and then you have to zero down to, let us say, here you have to zero down to, let us say, 2 or 3. Okay, then you have to zero down to 2 or 3. Okay, in this particular case, we zero down to 4, then we zero down to 3. Okay, so you have to zero down to particular. You have to look at overburdens. You have to look length of tunnel which is coming. Okay, you have to look at the geology which is coming. Okay, you have to look at traffic what is coming. So all that you have to do. After you have done that, then you have to look at what are approach roads, what is going to come, what is the length which is going to come, what is the implication of that. Okay, what are the maximum overburden, underburden, gradient, all that work has to be done. Once that is done, then you have to compare each of the alignment. Okay, each of the alignment has to be compared in detail with respect to geology. This is one table, but it has to be really compared in detail with respect to traffic, tree cover, water, building threats, okay, contractual issues, and then you have to come. Then you have to see which is the best one, and you have to come. Okay, then you start doing investigation. So at this stage, once you have done all these things, you require an approval. Once you have got this approval, then you are required to do a geological studies, and then after geological studies, you require to start your designing, and then from those designing, you will get your BOQs, you will get everything. Okay. Now, most of the cases, what happens is when you have finished this, then you come to option, whether you require an escape, you don't require an escape, whether you require 2-lane or you don't require a 2-lane. Now, important information which I want to give you, it should be here in this tunnel. Let us go ahead. Is if you look at excavation, okay, this is 2-lane bidirectional single tube with escape. This is 2-lane unidirectional. This is intermediate lane, okay, twin tube, and this is single lane twin tube, and these are number of lanes here. You can see 2 lanes in main tunnel, 1 in escape. Now, since this is 2-lane, so you have 2, you have 1. And if you look at volume of excavation, okay, you can look at volume of excavation. It's not much difference is not there. So what I'm trying to tell you is, that if you look here, it is 5 lakh 90. Here it is 6 lakh 66. Here it is 6 lakhs. Going for a main tunnel and escape tunnel is something which is very, very criminal. Okay, if you have to any time in life go for a main tunnel and escape tunnel, it is always better to go for a twin tube, because if you look at area of square meter of excavation, there is hardly any difference. Okay, later on, if we try to make an escape into a main tunnel, it is going to be a huge cost and it's going to be huge implication. So either we take a decision in case, if we want to take a risky decision, we take a decision of not making an escape. Okay, otherwise we always go with the twin tube. That's the one of the most beneficial decision which has requires to be taken. Then each of this cross section, this is what is shown. Okay, this is what is shown. I think I need not elaborate on this. Once this presentation is shared to you all, you can look at the cross section. Okay, this is what I was telling, elevated footpath. So if you look at elevated footpath, certain places I have seen elevated footpath being given on both the sides. And once you give elevated footpath on both the sides, if anything happens, it is very difficult to, mount. Especially imagine a lady wearing a sari. How she will mind and how they will run. And whole of this footpath may still have, whole of this carriageway may still have traffic coming in. So that are the challenges which are to be looked into. Okay, tunnel design is always about safety first. Okay, and emergency escape first when you design, and when you plan all the peripherals which are to be put inside. Then there are twin tube. Then there is a twin tube tunnel. Okay, so each cross section has to be looked into. Each cross section has to be worked on. Okay, each has to be decided, and this has to happen in preliminary. Now we are into last two slides. Okay, last two slides of my presentation, and I will close it here. Once this is over, okay, once you have decided, okay, before you go for a detailed design, these are the decisions one has to give when the alignment is getting approved. Okay, whether you want to go for 2-lane, bi-directional, 2-lane, unidirectional, intermediate lane, single lane. And as I have told you, we should always avoid going main tunnel and escape tunnel, because it does not give you a financial benefit. Okay. Pavement camber is another important thing, because in tunnel, it is not like road. If you have chambers on one side, your whole drainage plan and whole thing shifts. Okay, so pavement cambers, okay, camber and drainage are very complex inside tunnel. And number of places when you work on this, you will find in DPR, the things have not been taken into consideration, and during execution, then these problems are solved. Okay, these are very, very common in our industry, that drainage is solved during construction. Okay, and number of places we have faltered, and in those places those tunnels are still facing challenges. Then you have crash barrier. I said elevated. IRC SP 91 recommends it. Hopefully the revision should take it out. Okay, we should not have elevated footpath. You have to safeguard the people by only railing and crash barriers. Okay, on side. Okay, then curbstone. Then footpath. Okay, I said raised, not raised. Then railing heights. Okay, railing heights. If you are making railing heights, the railing should not be continuous. You should have gaps in between, so that in case of incident, people can get into and run away. Otherwise, people, I have seen the continuous railings are being made. Okay, then cross passages 500. Okay, lay-by and refuges for parking. Whether you require, you don't require, that is another going to be a big cost, because you increase the cross section. So these are the points which you require to deliberate when these files are on your table. These files are on your table, and you got to give a decision before the design starts. So with this, I come to my last point. Thank you. Okay, so that's all.